everyone, thank you so much for joining this video. Today we're going to be looking at the modification of alkanes by cracking. So cracking involves the breaking of carbon-carbon single bonds in alkanes, and we're going to learn about the two different types of cracking. So we have thermal cracking and catalytic cracking, and we're also going to be able to explain the economic reasons for cracking alkanes. Now we're going to talk about cracking. So cracking is the process of breaking down larger hydrocarbons which have been obtained from fractional distillation into shorter hydrocarbons by breaking the CC bonds in alkanes, so the carbon-carbon single bonds. So we break the carbon-carbon bonds and we're breaking down larger hydrocarbons into shorter hydrocarbons. So that is the main key point about cracking. There are a few economic benefits of doing this, and the first is that the petroleum or the crude oil fractions with shorter carbon chains, for example petrol, are in more demand than the larger fractions. And secondly, it makes use of the excess larger hydrocarbons because we don't find them as useful. And thirdly, the products of cracking are much more valuable than the starting materials. So for example, ethene used to make polyethylene or branched alkanes for motor fuels. So there are two types of cracking, and you need to know the difference between the two and also all of the different things which are different about them. So we're first going to go through thermal cracking. Thermal cracking takes place at a very high pressure, so around 7,000 kilopascals, and a very high temperature, so 400 to 900 degrees Celsius. It produces mostly alkenes, and for example, ethene, which we use to make polyethylene, which is a polymer, so ethene is the monomer, and ethanol. And it also produces hydrogen sometimes, which we use in the Haber process to produce ammonia, and also hydrogen can be used to manufacture margarine. The second type of cracking we have is catalytic cracking, and this happens at a slight or moderate pressure, so a lot lower than for thermal cracking. However, it still happens at a high temperature, so 450 degrees Celsius. And they also use a zeolite catalyst, which speeds up the reaction. Catalytic cracking produces branched cyclic alkanes and aromatic hydrocarbons, and these are valuable because they burn more cleanly. And catalytic cracking is used for making motor fuels. So you need to remember all the key points about these two types of cracking. So first we've got, for thermal, we've got a high pressure and a high temperature, whereas for catalytic, we've only got a moderate pressure, but a high temperature, and also the zeolite catalyst. So these are the conditions. And then you need to remember what they produce. So thermal cracking produces mostly alkenes and also sometimes hydrogen. And catalytic cracking produces branched alkanes and cyclic alkanes and also aromatic hydrocarbons. So aromatic meaning it has a benzene ring. And catalytic cracking is used for making motor fuels. So you have to remember these key points because you'll be asked about it quite a lot, and also to compare the two of them. Now we're going to look at some questions. So for question 1, 1 mole of compound Y is cracked to produce 2 moles of ethene, 1 mole of but-1-ene, and 1 mole of octane only. For A, deduce the molecular formula of Y. So this is just a case of working out what we started off with. So we have Y and we form 2 moles of ethene. So the formula of ethene is C2H4 because eth is the prefix for 2, so that's 2 carbons. So we have 2 moles of C2H4 and also 1 mole of but-1-ene, so that's C4H8, and also 1 mole of octane, C8H18. And now we just need to balance this. So we should have carbons and hydrogens. So for carbons, we have 4 plus 4 plus 8, which is 16. And then for hydrogens, we have 8 plus 8, which is 16, plus 18, which is 34. And so the product is an alkane, which we expected because we're cracking. And then for B, other than cracking, give one common use of Y. So because it's quite a long chain, actually it kind of stands in the middle of the fractional distillation column. And so we can use Y, so the C16H34, in kind of fuel oils, so motor fuels, and also maybe perhaps kerosene, which is the fuel used for aeroplanes.